So, good evening, all. Today we are going to discuss rearrangements part 2 for the IIT JAM 2024-25 tutorials of organic chemistry. So, last week we have started rearrangements and we have discussed regarding Wagner Marine rearrangement and Pinacol rearrangement as the major rearrangements. So, today we will continue with semi-pinacol rearrangement. So, in case of semi-pinnacle rearrangement, if we consider this isonopinon and we treat it with medial vitixol, it will result in the formation of this alkene. When it is subjected for osmium tetroxide treatment, it will undergo dihydroxylation reaction, resulting in the formation of this diol. And this is assumed to undergo some rearrangement, resulting in the formation of target ketone. So, if we consider protonation, this group will leave, and in the presence of this lone pair of electrons, this bond will break and it will shift towards here. It can result in the formation of this ketone. This reaction we are expecting, but it does not occur. So, what is forming here? So, for this reaction to take place, we have to first tosylate this primary alcohol. In tosyl chloride pyridine condition, it will undergo selective tosylation reaction of the primary alcohol. Then, after tosylation, when this lone pair of electrons on this OH will shift in this direction, this bond will break and it will shift towards this carbon. The OTS bond will break and it will leave. OTS is a better leaving group. So, this will take place in the presence of CaCO3, which is a mild base. Only tosylate can leave in non-acidic condition. Okay, that is why this reaction is taking place in this condition. It will result in the formation of this target ketone. So, this reaction that is taking place over here is known as semi-pinnacle rearrangement. So, if we see the major difference between semi-pinnacle product and the pinnacle product, we can see in the case of pinnacle rearrangement, the more hindered hydroxyl group will be leaving, leading to the formation of the stable cation. So, here this is if the hydroxyl group here will be leaving, it will result in the formation of a tertiary carbocation. If this hydroxyl group is leaving, it will result in the formation of a secondary carbocation. So, the formation of tertiary carbocation is preferred over that of the secondary carbocation. So, it will result in the formation of this carbocation. Then this lone pair of electron will push in this direction. This alkyl will shift to this carbocation, resulting in the formation of this um, carbonyl group, which upon deprotonation will result in this pinnacle product, which is this aldehyde. But i- if this group is undergoing tosylation in the presence of pyridine, so the less hindered hydroxyl group will undergo tosylation. So, here we have a tosylation tosylated alcohol. So, in the presence of base or under neutral condition, so in the presence of base, this proton will be abstracted. This lone pair of oxygen will shift in this direction. So, one of the R groups will migrate in this into this carbon, leading to removal of this OTS, which is a beta leaving group. So, it will result in the formation of the semi-pinnacle product, which is a ketone. So, as we can see here, since tosylation occurs at the less hindered hydroxyl group of the diol, not only can semi-pinnacle rearrangements be more regioselective than pinnacle rearrangements, but their regioselectivity may be in the opposite direction. So, semi-pinnacle rearrangements is taking place in regioselective manner because among the tertiary and the secondary, it will prefer over the secondary and it will regioselectively tosylate this secondary hydroxyl group, and then it will undergo the semi-pinnacle rearrangement. So, here the regioselectivity is in the opposite direction as that of the pinnacle rearrangement, as we can see from this example. Is this clear? Now, Coming to other type of semi-pinnacle rearrangements, we have seen the formation of aryl disonium salts. So the aniline, when it is treated with NaNO2 HCl condition, it will undergo diacetylation reaction leading to formation of this N3 plus Cl minus, which is a stable disonium salt. So the aryl disonium salts are stable, but the alkyl disonium salts are not. So the nitrogen gas, which is the world's best living group, and when it goes, it leaves behind a carbocation. So we can see here we are having a alkyl amine. So it will undergo in diazotization reaction in the presence of NaNO2 HCl, leading to formation of this disonium salt, unstable alkyl disonium salt. So the nitrogen gas, which is a better living group, will remove. It will result in the formation of carbocation R plus, which will undergo further reaction. So in this case of hydroxyamine, so here in the presence of NaNO2 HCl, this will lead to formation of N2 plus. Then this lone pair of oxygen will push in this direction. Then this bond will break and it will attack this carbon, leading to removal of N2 plus, leading to formation of this ketone. So this rearrangement where the amino alcohol this rearrangement, which is the amino alcohol counterpart of semi-pinnacle rearrangement, is known as Tiffinu-Dimjanov rearrangements. So it is a form of semi-pinnacle rearrangement only. Tiffinu-Dimjanov rearrangement. Now we are having a disonium salt. So if we are abstracting a proton of this disonium salt, it will result in the formation of this diazo compound, which can be mm, which can be represented in this form as well. Like when the lone pair on this nitrogen will shift here. So here a negative, here already a positive charge is there, okay? Since the nitrogen is having 4 valency, it is positive charge. So this is the diazo compound, diazoalkane, which will be resulted upon deprotonation. So now, when the diazomethane will attack on the ketone of the cyclohexanone, it will result in the formation of this intermediate. So this lone pair of oxygen, when it will be shifting here, this bond will be breaking and it will attack at the center, leading to removal of N2 gas, which will result in the formation of this uh, ring expansion product. Cyclohexanone is converted into cycloheptanone. Ring expansion by insertion of one CH2 group. This is also a kind of semi-pinnacle rearrangement. Now coming to next type of rearrangement, that is dienone-phenol rearrangement. So we can see in this reaction the dienone that is present at this center, in the presence of acid medium, it is converted into phenol. So we will see how it is taking place. So this type of rearrangement is known helpfully as a dienone-phenol rearrangement, and we can consider it quite simply as a type of reverse pinnacle rearrangement, because in the pinnacle rearrangement we have got a carbonyl group at the end, and in this case the carbonyl group is getting converted into alcohol. In pinnacle rearrangement, alcohol is getting converted into a carbonyl, and here the carbonyl is getting converted into a alcohol. So that is why we can consider it like a reverse pinnacle rearrangement. Now, pinnacle and semi-pinnacle rearrangements are driven by the formation of a carbonyl group. The rearranged cation is stabilized by being next to oxygen, and it can rapidly lose H plus to give the carbonyl compound. So this is what is taking place in the pinnacle and semi-pinnacle rearrangements. But in the key step of a dienone-phenol rearrangement, a protonated carbonyl compound rearranges to a tertiary carbocation. So we will see the mechanism of dienone-phenol rearrangement in the next slide. So this is the mechanism of dienone-phenol rearrangement. We are having a dienone in the presence of H plus. This carbonyl group will get protonated. So this protonated ketone, it will rearranges to form a tertiary carbocation. So this methyl group will shift to this position. This double bond will break and it will shift to this position, and it will neutralize the positive charge on the oxygen, leading to formation of an alcohol. Now we are having a tertiary carbocation. For neutralizing it and for the regaining of aromaticity, this proton will be abstracted. It will be moving in this direction so as to neutralize the positive charge, resulting in the formation of phenol. So the protonated ketone rearranges to tertiary carbocation, and loss of H plus gives an aromatic compound. These are the two major steps that is taking place in dienone-phenol rearrangement. So the reaction is driven from dienone to phenol because the product cation can rapidly undergo elimination of H plus to become aromatic. So the gaining of aromaticity is one of the driving force for the dienone phenol rearrangement to take place. So here there is one question based on dienone-phenol rearrangement. What is the major rearrangement product of the following reaction? So this is our dienone, and it is treated to H plus condition. So it will result in the formation of any of these four products. So we have to identify the product. So this is A, B, C, and D. What is the major rearrangement product that is formed in this reaction? So coming to the mechanism of the reaction, we are having the dienone in under protonation condition. This ketone will get protonated, and then migration of this group will take place to the center. This double bond will shift here, and this carbonyl group will break, leading to neutralization of the positive charge on oxygen. So we are having this intermediate. Now in order to regain the aromaticity, this proton will be abstracted, leading to formation of this phenol. So a dienone to phenol rearrangement is taking place. So the right answer will be option A. Now coming to benzylic acid rearrangement. So we have seen rearrangements in which the carbonyl groups form at the migration origin, like pinacol and semi-pinacol rearrangement. So the migrating group in the pinacol and semi-pinacol rearrangements is pushed by the oxygen's lone pair as it forms a new carbonyl group. Now you have seen the carbonyl groups being destroyed at the migration terminus. The migrating group at the dienone-phenol rearrangement is pulled towards the protonated carbonyl group. So the protonated carbonyl group is getting destroyed at the migration terminus. So the first rearrangement reaction ever to be described as both of this at once is the benzylic acid rearrangement. So in benzylic acid rearrangement, the carbonyl group is getting formed as well as it is getting destroyed, as in the semi-pinacol pinacol rearrangement and dienone-phenol rearrangement. So we can see the mechanism here. So this is the benzyl. When we treat it with OH minus and then protonate, it will result in the formation of this benzylic acid. So here two ketones are there. So this is getting oxidized to carboxylic acid, and this is getting reduced to alcohol. So as we have seen, the formation of double bond O is taking place, carbonyl is taking place, as well as destruction of carbonyl is taking place. So we will see the mechanism of benzylic acid rearrangement. So in the presence of OH minus, it will add to one of the carbonyl, and it will result in the breakage of this O minus. Now we are having this intermediate, then this O minus will be pushed in this direction. So the carbonyl group is formed here, and this phenyl will migrate to this carbonyl, and this C double bond O pi bond is broken here. So the carbonyl group is forming here, as well as the carbonyl group is broken here. So it will result in the formation of this benzylic acid. Upon deprotonation, this reaction will become irreversible. So one other such reaction is this. So the tertiary butoxide is the nucleophile here. It will add on to this sender. We will this carbon oxygen bond will break, and we will get an intermediate similar to this, where pH double bond O O minus, pH, O, T, Bu is formed. Now, once this oxygen lone pairs is coming here, this pH bond will migrate onto this and it will result in the formation of this product. Now coming to the next sort of rearrangement, which is the Favorskii rearrangement. So the Favorskii rearrangement is a rearrangement of an alpha haloketone to an ester. So here we can see this halogen is present at the alpha position of this carbonyl group. So this alpha haloketone is getting converted into this ester. So when we compare the Favorskii rearrangement and the benzylic acid rearrangement, which is the rearrangement of a diketone to an ester. So when we see this, here this rearrangement involves breakage of the CX bond, and in this this rearrangement involves the breakage of the C double bond of bond. So when we see these two reactions, it superficially they seem similar, but mechanistically they are quite different. So when we are considering this alpha halo ketones, these both alpha haloketones, they are resulting in the formation of the same product. So the mechanism of this reaction is somewhat different. From this we can understand that the mechanism of the reaction is somewhat different from that of the benzylic acid rearrangement. So if we are having a proton here, and the methoxide will abstract this proton, result in the formation of this enolate. So we are having this enolate here, and this enolate, when it is falling back, and this carbon carbon double bond will go and attack at this position, and the Cl minus, which is a leaving group, it will eliminate, leading to formation of this cyclopropanone. And in the other case, methoxide will abstract the proton from this carbon, leading to formation of this enolate. And when this is going back, this O minus is pushed in this direction, this carbon carbon double bond will go and attack on the CCl bond, and it will break, leading to removal of Cl minus, and it will result in the formation of this same cyclopropanone. Now, having this cyclopropanone in hand, the OMe will add on to this carbonyl group, and this CO double bond will break, and once this O minus is falling back, this bond will break and it will protonate, leading to formation of this ester. So this is the mechanism of Favorskii rearrangement. If you are having any doubt regarding Favorskii rearrangement, we will see while solving the questions. So we can see we are having a cyclohexanone. When it is treated with Br2 and acetic acid, it will result in the formation of alpha bromo compound. And now we are having the alpha haloketone, which is the starting material for Favorskii rearrangement. In the presence of a nucleophile or base like NaOMe, it will result in the formation of this ester. So we will see the mechanism. So the proton, the alpha proton will be abstracted by OMe, then the enolate will be resulting, and this O minus, once it is falling back, this carbon carbon double bond will go and attack on the CBr, on the antibonding orbital of CBr, and the Br minus will leave. It will result in the formation of the cyclopropanone. Then OMe will be attacking at this carbonyl group, then electron pushing will occur in this direction, and this bond will break and protonate, resulting in the formation of this ester. So what is taking place in Favorskii rearrangement is that the R group that is present here migrates from one side of C double bond O to the other side. So this is what is basically taking place in Favorskii rearrangement. And one of the advantage of Favorskii rearrangement is that Heavily substituted acids where CO2H, that is attached to a tertiary carbocation, would be hard to make by any other method. So for making heavily substituted acids, that is CO2H that is present in the tertiary carbon, can be prepared by this method. So two examples are this alpha haloketone. When treated with KOH, it will result in the formation of this acid, which is a tertiary carboxylic acid. Similarly, in this case, when it is treated with NaOH, this alpha haloketone, it will result in the formation of this acid, which is also a tertiary carboxylic acid. So, semi-benzylic Favorskii rearrangement of non-enolizable ketones. So, non-enolizable ketones can also undergo Favorskii rearrangement, but it will be a sort of semi-benzylic type of mechanism. So here what is happening, the OH minus will be directly attacking on the carbonyl, the C double bond or bond will be breaking. Since there are no protons, so we cannot form the enolate. So it will attack, O minus will be forming, and once this O minus will fall, this phenyl group will migrate to this position, and this CCl bond will break and Cl minus will leave, leading to formation of this product. And NaOH can abstract the proton of this carbonyl so as to make the reaction irreversible. Now coming to solving the previous year questions. So this is a question from JAM 2019, which is a one marker question. So the correct option for major products of the following reaction is. So we are having a labeled carbon here which is adjacent to the Cl, and it is treated with NaOET ethanol. So as we know, this is the alpha haloketone and it is treated with the base cum nucleophile NaOET. So what is the rearrangement that can take place? Obviously, as we have seen in the previous slide, it is a Favorskii rearrangement. So it will result in the formation of two products based on where the which bond will be breaking of the cyclopropanone. So based on that, we will be getting two products, and we are asked to identify which is a major product. Okay. So the correct option will be option C, and we will see the mechanism of how this answer is resulted. So we are having this compound in the presence of NaOET. The proton here will be abstracted by OET minus. It will abstract the proton, resulting in the formation of this enolate, and once it is falling back, this carbon carbon bond will go and attack on the antibonding orbital of CCl, resulting in the removal of Cl minus, and it will result in the formation of the cyclopropanone. Then OET minus will attack on this carbonyl carbon, resulting in the formation of this tetrahedral intermediate. Once it will collapse, it can result in the breaking of this bond or this bond. When this bond is breaking, it will result in the formation of this product where the COET is present on the carbon adjacent to this labeled carbon, and once this red this bond marked by the red arrow is breaking, it will result in the formation of this compound where COT is present on the carbon that is labeled. So this is the right product. Now coming to another question. On the reaction with NaNO2 and HCl, which of the following amino alcohols will yield yield compound P? So this is the product, and we are asked under NaNO2 HCl condition, that is diazotization reaction will be taking place. So this will result in the formation of N2 plus, which is a good leaving group. So which of these four compounds or amino alcohols will result in the formation of the compound P? So this is a sort of Semi-Pinacol rearrangement or Dienone rearrangement, as Dienone sort of rearrangement that we have seen. So the answer will be C and B. When NH2 is treated with NaNO2 HCl, it will result in the formation of N2 plus. So this will result in the formation of N2 plus. So this bond is anti-periplanar to the leaving group, and here also this bond is anti-periplanar to the leaving group. So once the oxygen is falling, in either case this bond can shift, and it will result in the removal of N2 plus, and we will get this desired product. Okay. And another question which is from JAM 2016, a one marker question. So here we are given a question based on Pinacol rearrangement. So we are having a asymmetric sort of system, and it is treated with H2SO4. So what is the major product that we will get? So it will depend upon the stability of the carbocation that is forming. Benzylic carbocation is more stable, so it will be forming. So the answer will be B. Here this OH2 will be leaving, positive charge will be forming, and when this oxygen will fall, this group will go and attack at this position, resulting in the formation of the 7-membered ketone, as you can see here. So this OH2 will get protonated and it will leave, and here a benzylic carbocation will be forming. This lone pair on oxygen will migrate, and this bond will break and it will shift to this position, resulting in the formation of this product. So that's all for today. Thank you. If you are having any doubts, you can feel free to ask in comments.